Okay, the topic now is hypothesis testing. All right, let's start. So before we start with the statistical hypothesis, let us first define what a hypothesis is. So a hypothesis is basically defined as an educated guess. But what do we mean exactly by educated in the given definition? It means that the guess that you're giving out is based on facts, based on information, based on current knowledge or a common knowledge. So it's a guess because it still needs to be tested or it still needs to be proven. So though it's a guess, it is based on facts, unlike wild guesses that are just like random guesses. Okay, so that's what a hypothesis is. So for statistical hypothesis, it is defined as a conjecture about a population parameter. This conjecture may or may not be true. Okay, so there are two types of hypothesis for the hypothesis testing. So the first one is called the null hypothesis. It is a statistical hypothesis that states that there is no significant difference between a parameter and a specific value, or that there is no significant difference between two parameters. Okay, so the important part here is that there are no significant difference, because when we are comparing two groups of values or two groups of distributions or two groups of data, it is sometimes bound to have differences. They might not be exactly the same. So there might be differences. So what we're testing here is that difference between the two groups significant enough to say that it is not due to chance. Okay, so the term no significant difference is very important. So the other hypothesis is called alternate or alternative hypothesis. So it is a statistical hypothesis that states that the existence of a significant difference between a parameter and a specific value, or states that there is a significant difference between the two parameters. So just the uh, uh, negation of the null hypothesis. So no significant difference for null hypothesis. For alternate hypothesis, there is a significant difference. Okay, so take note that when two groups being compared, it has no significant difference, then it can be said that they are statistically equal. Okay. So examples of hypothesis. So a medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after the patient takes the medication? So assume that the mean pulse rate of the population is 82 beats per minute. So we know this one, the 82 bits per minute, it's considered to be a common knowledge with regard to the pulse rate. Okay, so it's like a known fact that the average beats per minute is 82. So the situation is that the medical researcher wants to test if there will be undesirable effects. So he just wants to know if there will be either an increase, a decrease, or will the beats per minute remain unchanged. So the null hypothesis will state that there is no significant difference or no significant change in the average pulse rate of the patients. So if uh, the tests, okay, will show that there is no significant difference between the test results and the known average, which is 82 bits per minute, then we can say that there is no significant difference. Okay, so the alternate hypothesis will state that there is a significant difference or change that would either be an increase or decrease, as long as there is a significant change, right, in the pulse rate of patients. Therefore, we can say that the average is not equal to 82 because there is an increase or there is a decrease. Okay. So another example, a chemist invents an additive to increase the life of an automobile battery. If the mean lifetime of the automobile battery without the additive is 36 months, then her hypotheses are So HO will state that there is no significant difference or no significant change in the average lifetime of the battery. So mu will still be equal to 36. Mu is the population mean, which we know the population mean is the average values of the whole population. All right, so that's mu is equal to 36, which is the given 36 months. So again, HO will always state that there is no significant difference. Okay, and then H1 or the alternate hypothesis will state that the average lifetime of the batteries will increase. Thus, H1 mu is greater than 36 because that is the claim of the study. So the additive will increase the life of an automobile battery. That's what the test is all about, to check if there will be an increase. Okay, so example 3. So a contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, her hypothesis about heating costs with the use of insulation are, so the HO will state that there is, again, no significant difference or no significant change in the average monthly heating bills. Thus, mu, or the population mean, is still equal to $78. And then, with the special type of insulation, it will state that the average monthly heating bills is decreased or will decrease. So mu is less than $78 because if the special type of insulation is effective, then the heating bills will be lowered. So that will become lower than 78. And that should be significantly lower than 78 so that we can have this. Okay, so as you can see, the first example we had mu is not equal, the other one is mu is greater, and then this one mu is less. Okay, that is because of the different claims or different goals of the test. One test shows that it's not concerned about whether one group is less or the other group is greater, as long as there is significant change. That's when we use the not equal symbol. While if the test is indicating a direction in terms of the comparison, it says that one group will be less than the population mean or than the other group, then we use less than. Or another is that when the comparison is concerned about whether one group is greater than the other, then we use a greater than. And that leads us to the next one. So the types of tests based on direction. Okay, so we have what we call here the one-tailed test, because this test indicates that the null hypothesis should be rejected when the test value is in the critical region on one side of the mean. A one-tailed test is either a right-tailed or left-tailed test, depending on the direction of the inequality of the alternate hypothesis. So the one-tailed test is based on the direction of the test being done, whether it shows a less than or greater than, okay, especially in the alternate hypothesis. You can always see that in the problem if the problem states that one group is less than the other, or if it is testing that one group is greater than the other, then that is automatically a one-tailed test. So we have here a right-tailed or left-tailed test. Of course, it will be a left-tailed test if we're talking about a less than, while it's a right-tailed test if we're talking about greater than. Okay, and then of course the other one. So here it's a left-tailed test. The shaded region or the critical region will be on the left side. Right-tailed test is on the right side. So what is that critical region? Later on in the topic, we will be discussing that as well. So for the two-tailed test, so the null hypothesis should be rejected when the test value is in either of the two critical regions. So this time, both on the left and right, because we have a two-tailed test. This happens when the claim of the study is just trying to know if there is a significant difference, whether it's less or greater, whether it increase or decrease, as long as there is significant change. That's why we have a two-tailed test. So both ends, whether it's a decrease, that will be on the left side, or an increase, that will be on the right side. So either way, that is your two-tailed test. All right. So now, how do we identify the critical regions? So the critical regions depend on the level of significance and the type of statistical tool to be used. There are different types of statistical tools, or what we call statistical tests. So for starters, we have the z-test, or the one sample z-test, and the one sample t-test, or the independent samples z-test and the independent samples t-test, and some other tests. So the critical regions is based on the level of significance and what type of statistical tool you will be using for your hypothesis testing. So for now, let's define what the level of significance is. It is the maximum probability of committing a type 1 error. So we use the symbol alpha, or the Greek letter alpha. So what does it mean? It's a level of significance is the maximum probability of committing a type 1 error. That means this is the chance, the small chance that we might commit a type 1 error. But what is a type 1 error? So a type 1 error occurs if you reject the null hypothesis when it is actually true, while a type 2 error occurs if you don't reject the null when it is actually false. Okay? So so for hypothesis that you rejected when it is actually true, then that is a type 1 error. While on the other hand, the other one is the type 2 error. So we have here practice exercises. So a researcher wishes to see if the mean number of days that a basic small automobile sits on a dealer's lot is 29 days. So a sample of 30 automobile dealers has a mean of 30.1 days. At an alpha of 0.05, test the claim that the mean time is greater than 29 days. The population standard deviation is 3.8 days. As you can see, there are numbers given here that we haven't used yet because at first, we need to understand how to create or how to write our null and alternate hypothesis and the type of tail tests. So here, there is no significant difference between the population mean, which is the 29 days, because this is the common knowledge, or this is what is known about how many days the automobile stays in the dealer's lot. This is what they know. That's 29 days. And the sample mean of 30.1 days. This is the test, basically. So it took a sample of 30 automobile dealers, and the mean number of days showed was 30.1. So now we are comparing the 29 days and the 30.1 days. So what is the claim of the study? So the claim is that the mean time is greater than 29 days. So the researcher wants to show that it's not 29 days, but it should be higher. So the sample size of 30 shows a mean of 30.1 days. So what we need to prove here is that 30.1 days is actually significantly greater than 29. So that's why the mean number of days is greater than 29 days. That is our alternate hypothesis. So we can only say this. We can only say that the mean number of days is greater than 29 is if we can prove that 30.1 days is significantly higher than 29 days. Then we can say that the mu should be greater than 29. Right? And because of that, this is a one-tailed test, and specifically a right-tailed test because of the greater than. All right. Next. So a researcher claims that the average cost of men's athletic shoes is less than $80. He selects a random sample of 35 pairs of shoes from a catalog and finds the average cost to be only $75. Is there enough evidence to support the researcher's claim at an alpha of 0.1? Assume the population standard deviation is 19.2. So in this case, the problem shows that a researcher claims that the average price of athletic shoes, it should be less than $80. So, but to test that claim, he chose 35 pairs of shoes from a catalog randomly, and he found out that the average is only $75. So what we need to show is that $75 significantly lower than $80? So HO, there is no significant difference between the means, which is the $80 and the $75. So if there is no significant difference between those two averages, then we can say that the average really is equal to $80. While the H1, which always states that there is a significant difference, would say that the average cost is less than $80 because again, you can only say that if we can prove that the 75 is significantly less than 80. So therefore, mu is less than 80. Or we can say that there is a significant difference between the population mean of $80 and the sample mean of 75. So again, this is a one-tailed test, specifically a left-tailed test because of the less than here. Okay. And then this one, a researcher claims that the average wind speed in a certain city is 8 miles per hour. So a sample of 32 days has an average wind speed of 8.2 miles per hour, and the standard deviation of the population is 0.6 miles per hour at an alpha of 0.05. Is there enough evidence to reject the claim? So again, what's the study? The researcher sees that the average wind speed is 8 miles. That's his claim. This is 8 miles per hour. Okay, so we want to see if he is correct. Okay, so a sample of 32 days doesn't show an average of 8.2 miles per hour. So is that 8.2 miles per hour significantly different than the claim of 8 miles per hour? Okay, so there is no significant difference between the average wind speed from the claim of the researcher, which is 8 miles per hour, and the sample mean, which is 8.2 miles per hour. So if there is no significant difference, then we can say that mu is actually 8 miles per hour. Okay, so there is a significant difference in the average wind speed in the city. If we can prove that 8.2 is significantly higher than the 8 miles or significantly different than 8 miles, then mu is not equal to 8 miles per hour. Why not equal? Why not use 8.2? Why not use greater than? Since 8.2 here is greater than 8, right? So why not use a greater than? Because that is not what the researcher wants to test. The researcher only wants to test his claim that the average wind speed is 8 miles per hour. He's not concerned whether it's greater than 8 or is it less than 8. Okay, so it just wants to prove that it is 8 miles per hour. Okay, so if you can say that the 8.2 miles is significantly different than 8 miles, then you can say that it is not 8 miles per hour. Then his claim is not true or is rejected. All right, so that will be a two-tailed test because there is no direction. There's no less than or there's no greater than claim. Okay, so you can answer this on your own. So if you want to try, okay. So that's it.